This is problem 82. It's our last example problem from the electric field section. Two large metal plates of negligible thickness are separated by a distance of 2d and are parallel to the xz plane. The bottom plate has a charge density of sigma and the top plate negative sigma. Find the electric field at all points on the y-axis and sketch the y component of the electric field on the graph at right. Okay, so I'm going to show you how this works. This is for two large metal plates, so I would call these parallel plates, and we're going to see parallel plates again later on in this course. I'm not really that interested in following the steps that they give me here for Gauss's law, because we just did something similar back here. I do want to figure out what the electric field is when y is less than d. So they're separated by a distance of 2d. They have negligible thickness, which makes this a little different than what we did in the problem over here. And here we had sigma on the top surface and the bottom surface. So that would be for one plate here, this total surface charge density would be 2 sigma, because you have sigma on the top and sigma on the bottom. Here you have sigma on the whole plate. Here you have sigma on this whole plate. So one plate has a surface charge density of sigma, which is half of what we had in the previous problem. So keep that in mind. We're looking when y is less than little d here, so we're looking there. And we want to know the electric field. I'm going to kind of cheat when I do this because we already saw how Gauss's law works out in this situation on the previous page. So I'm just going to look at one plate. I'm not really going to follow what they tell me to do on the worksheet in order to solve the problem, but I do want to see what I get for the electric field when you have one plate with a charge sigma. So doing something similar to what I had on the previous page, I have my Gaussian surface here. And just for this, so I'm ignoring the bottom plate now, and I'm going to look at that later. An expression for the surface area parallel to the electric field. Well, the electric field would be pointing this way and this way just from this one plate. So the surface area would be the area of this face and this face. We're going to call that 2a. So that's similar to what we did over here where we had 2a. But now Q enclosed is not 2 sigma a because we don't have charge here and here. We just have charge on this plate of negligible thickness. So this is going to look now like this, where it's negligible thickness and the surface charge density is just sigma. So Q enclosed is equal to sigma times A. And then if I do EA is equal to Q enclosed over epsilon naught, I get E is equal to Q enclosed, which is sigma A divided by A, and epsilon naught. Whoops, I went too fast there. Write an expression for the surface area parallel to the electric field. That's the area that you have here. So A is equal to 2A. So I have 2A in the denominator here. So I have the electric field is equal to sigma over 2 epsilon naught, which just happens because here the charge on the one plate was 2 times sigma because you had sigma on the top and sigma on the bottom, and here the charge on one plate is just sigma. So this is for one plate, and then I'm going to use the superposition principle to figure out the electric field everywhere. So the superposition principle says E net is equal to E1 plus E2. In this case, we just have two electric fields. So that's going to be all we need. Okay, now the electric field, remember, it doesn't change as you go far away. So it's a uniform electric field. It's pointing away from the plate, and the magnitude is not changing. So for this plate, I have an electric field pointing away from the plate, and down here away from the plate. For this plate, I have an electric field pointing away and away and up here, away. And now I see that I didn't read the problem carefully. So the bottom plate is supposed to have a charge density of plus sigma, and the top plate has a charge density of negative sigma. So you can ignore what I just did there, and we're going to move on to this picture and do this again. So if this bottom plate is plus sigma and the top plate is negative sigma, then we're going to do this again, pointing towards, because it's negative sigma, the field would point towards. So that's not what I said here because I had sigma instead of negative sigma. So for this one, it would be negative sigma to epsilon naught, which would mean instead of pointing in the j hat direction, it's pointing in the negative j hat direction when we're above the plate. But we know it's always pointing towards the plate. Let's just say it's pointing towards and towards. And then for this one, because it's positive charge, it points away. So away and away and away. Okay, now the magnitude is the same. So this would be sigma over 2 epsilon naught. Same magnitude. Here, same direction. So here, the fields add. Here, the fields cancel. And here, the fields cancel. So this is the way I'm going to answer the question. I'm going to say we have this magnitude for each plate, canceling out here, so when y is greater than d, the electric field is equal to 0, and when y is less than d, let's just put this down here, when y is less than d, the fields add together, so that'd be sigma over 2 epsilon naught, plus we don't really have to worry, well, maybe I should just say the magnitude of the electric field is this. So that's the magnitude, and we took care of the direction there. So sigma over 2 epsilon naught plus sigma over 2 epsilon naught is sigma over epsilon naught. This is in between the two plates because they have opposite sign. If they had the same sign, the fields would cancel out in between the two plates, like I incorrectly did over here. So when y is less than d, we get this, it's constant. And then when we're outside the two plates, it's 0. Okay, so this is the electric field for parallel plates, where each plate has a charge of sigma. And that concludes the electric field section.